Welcome back everyone. In this lecture we will actually revisit the Casimir operators. So we need to actually make some observations about them. So let us actually start with why we actually defined Casimir operator. So let V being any finite dimensional G module. So G you take it to be, for example, any finite dimensional Lie algebra. So you can also assume to be JLN or SLN. Okay. So one can take any finite dimensional reductive Lie algebra or semi-simple Lie algebra, or here we can simply take G to be list, JLN or SLN. So now if we have a finite dimensional G module, if we take any G module homomorphism from V to V, so let us call it omega. So it is G module map. So then we observe that this omega actually commutes with the action of G. So because of that, if we take any generalized eigenspace of omega, that is going to commute with the action of G. Sorry, that becomes G submodule. Okay, so if we take any, so given any lambda in C, so let us take V lambda to be the generalized eigenspace corresponding to lambda for the operator omega. So then it is a easy exercise to prove that V lambda is indeed G submodule. Okay. So one can actually generalize this for other operators also. For example, if I have some other operator phi, let us say defined from V to V, assume that phi and omega commutes. So then if you take kernel of phi, so which is those vectors in capital V such that phi of V is 0. So then you can see that this kernel phi becomes G submodule. So this is just a map, C map. Okay. Okay, this must be a G module map. So let us write down what we want to do. Okay, so we want to climb this kernel phi to be actually G module. Okay, so let us take x in G and V in kernel phi and then try to compute what happens and then see. So let us assume that phi and omega actually commutes and omega is G module map. So now if we just compute what will be the xv and then if we apply phi, so then you can see that the omega phi xv is nothing but phi of omega xv. So now using that the action of G commutes with omega, or omega is a G module map, you can see that this is exactly phi of x omega of V. So now if we actually assume this x actually commutes with this phi, then you can just commute this x phi omega of V. Now again phi omega commutes, so it becomes x omega phi of V. So then this becomes 0 because V is coming from the kernel. Okay, if you take this to be G module map, then phi and omega commutes, then it is easy to see kernel phi is indeed is a G module, G submodule. Okay, so this is actually gives us a way to actually decompose V into G submodules. If we take any G module map, if we look at generalized eigen subspaces, and then we can write V as a direct sum of generalized generalized eigenspaces for omega, that is called primary decomposition of V with respect to omega, and that gives you G model decomposition of V. Okay. So, that is why we were actually looking for some operators that actually commutes with the action of G. So, that was the motivation to look for the operators, and then we define the Casimir operators corresponding to some representations. So, now let me make a theorem, because this is whatever we observed is going to be a very important result about representations of G. So, let us record it. So, let us call it a theorem. So, here we actually work with a very general setting. So, let V be a finite dimensional G module, and let B be a non-degenerate G invariant bilinear form. On G, let us say. So, then given a basis, okay, let us fix some basis x1 etc. xn. So, this is the basis of G. So, we can actually talk about dual basis of this. So, let us call it y1 etc. yn. So, now so this is with respect to the form. So, now we can define this Casimir operator. So, let us define this Casimir operator, which is acting on this V. It is an endomorphisms which is given by summation xi yi of V, where I range from 1 to n. This is you define for any V in capital. So, this is the formula that we have already seen defines the Casimir operators with respect to this bilinear form B that is defined on capital V. So, we already proved that this is indeed a G module map, okay, because it is coming from this non-degenerate form. So, now we are going to actually see whether it depends upon the choice of the basis or not. Okay. So, we have made this choice. So, we can actually see it is indeed independent of the choice of the basis. So, one can prove that the CB of V is a G module map. So, that is a first statement, and not only that, this is independent of the choice of the basis. So, that is independent of x1 etc. xn. Note that once you fix x1 etc. xn, then this y1 etc. yn that is already fixed, okay, with respect to this bilinear form B. So, let us verify this. So, we already did this calculation. So, that CB of V is indeed a G module map, okay, that I will leave it to you to again check. So, now we will actually prove the second statement. The second statement is indeed telling you that if we take actually another basis, let us call it z1 etc. zn, then if you define this Casimir operator with respect to that, so then the value of this Casimir operator will not change. So, that is what we need to prove. Okay. So, more precisely, so let us prove the second statement. So, let z1 etc. z1 be another basis of capital V. So, and then we can actually fix u1 etc. un to be its dual basis. So, now what we need to prove? We need to prove that if we take this operator xi yi acting on V for this summation xi yi, the value of this should be same as the value of zi uy acting on V. Okay. So, then this proves actually these two operators are same. So, that means the operator CVB is independent of the choice of the basis that we have chosen. So, this is a simple computation. Basically, we need to actually understand the transaction matrix that one can actually define for this xi to zi and then yi to ui. So, let us actually call those matrices A and B and then actually just observe what will be the relationship between them. So, let us call this translation matrix, okay, that actually maps xi to these zi's. So, this matrix we call it A. So, this is the translation matrix. Okay, by definition, so you are writing zi's in terms of xj's. Okay. So, if you write zi's as sum of xj's, then you have the coefficients, let them call that aji. So, that aji forms the matrix capital A. So, this is zi equal to summation aji xj, where j ranges from 1 to n. So, this matrix capital A is given by aij. So, now if we take this yi's and then let us say the transaction matrix to be B, which actually sends transfers to ui's. So, then you can see that again by definition. So, this ui is written by summation some bki yk, where k ranges from 1 to n. So, then B is given by this bki. So, basically we are taking the translation matrices of this corresponding base changes. So, now let us compute what will be the relations between the coefficients aij and bkj using this bilinear form. We know that it is G invariant symmetric bilinear form. So, G invariant symmetric and non-degenerate bilinear form. So, because xi yj's are dual basis, we know that the B of xi yj is given by delta ij. Similarly, B of zi uj is also given by delta ij. So, these relations we know, and B of okay, let us just start the computation. We want to just understand what is the relationship between bki and aji. So, let us look at this B of ui zj. So, because the matrix is the B is a symmetric bilinear form, this is same as B of zj ui, which is given by the chronicle delta ij. So, this you can rewrite. So, now compute this. So, ui you can rewrite as this. So, this is summation bki yk k range from 1 to n. Then you can rewrite zj as summation arj xr r range from 1 to n. Okay. Now, use the bilinearity and then just take out the coefficients, and then you can see that. So, this is going to be delta ij equal to summation bki arj b of yk comma xr. But again b of yk comma xr will be delta. So, this is going to be equal to this quantity delta kr. So, here the sum runs over k and r, which is running over from 1 to n. So, now you can see that whenever k equal to r, you get exactly 1, or otherwise this b of yk xr coefficients are 0. So, then you get exactly equal to summation bki a kj, where k range from 1 to n. So, basically this equation what it says. So, this equation actually tells you that these matrices A and B are closely related. Indeed, B is the inverse transpose of capital A. So, let us just write this. So, B is the inverse transpose of capital A. So, if we use this thing and then if we calculate for any V in capital V, we can see that the summation zi ui of V, where I range from 1 to n. So, this is going to be exactly equal to summation. So, now we can write zi and ui in terms of xi and yj's. So, just use that formulas and then rewrite this. So, then you can see that this is exactly aki bli xk yl with acting on V, where k I L all running from 1 to n. Okay. So, this just uses the formula zi equal to summation aki xk, and similarly ui is equal to summation bli yl. Okay. Use this formula to get this. So, now we can actually see that this is exactly equal to. So, whenever you see this ij running over here, so bki summation bki akj is going to give you delta ij. So, you are going to get exactly for if you run it over I. So, then this is exactly summation kl runs over 1 to n delta kl xk ylv. So, which is exactly equal to summation xk yk of v, where k range from 1 to n. Okay. So, just we are using the relationship between these coefficients of capital A and capital V. So, this proves that. So, this summation zi ui acting on V is same as the summation xk yk acting on V. So, this proves that as required the Casimir operator is well defined, which is independent of the basis that we choose in the beginning. So, these CBV, they are all called Casimir operators. So, this we have already seen. So, now once we have some non-degenerate bilinear form on G, then we are able to actually create Casimir operators. But the only thing that we do not know whether these Casimir operators are 0 or non-zero. Okay. So, that is the non-trivial thing that we need to determine. Okay. So, that is why we used for example, when G is SLN, we actually define the Casimir operator corresponding to the representation, and then using that we actually saw that just to say the Casimir operator is non-zero, we needed to show that the corresponding trace form is indeed non-degenerate. So, for that we had to use the non-trivial fact that the Cartan criteria for the solubility. Okay. So, that we could not avoid. So, it is indeed a big task to say this Casimir operators are non-zero. But if given representation, one will be able to compute it without any difficult. So, let us actually do that examples. So, because we are only interested in GLN or SLN, so let us do some basic computation. So, let us take G to be GLN. Sorry. So, we can take B to be the trace form. So, what that means, we can take B of xy to be just a trace of xy. Okay. So, GLN acts on Cn naturally. So, basically this trace form is associated with that natural representation. So, we are treating elements of GLN as matrices, that is all it means. So, if we take this trace form, and it is easy to see that this trace form is indeed non-degenerate. So, maybe I will leave it as exercise. Verify B is non-degenerate. So, not only that, if we take the standard basis Eij, so then its dual will be Eji. What does it mean? So, if we take the trace of Eij, Eji, then you get exactly we have to change the notations. This is not what we meant. So, we take Eij. So, because the indexing set is just in cross in. So, here the basis is, we are talking about the basis of GLN. So, this is the basis. So, the indexing set is in cross in, which is 1 to 1 cross 1 to n. So, we have to actually take that. So, in particularly here we get EKL, and then you get delta Ij KL, delta function defined on that. Okay. And this is easy to see actually. So, now if we take this trace form, then you can actually easily compute. So, what will be the Casimir operator corresponding to this trace form on the natural representation. Okay. So, take V to be Cn. So, GLN acts on Cn, and this is indeed irreducible module. So, it is G action is irreducible. So, now we know that the Casimir element must act as scalar on this GLN. Okay. So, I will leave it to you to check if we take this Casimir element with respect to this trace form on this representation Cn. So, this is going to be n times identity on Cn. Okay. So, this is what we get. Okay. So, we already know from Schur's lemma this must act as identity. So, it is not that hard to prove that this is indeed identity. So, another example, again you take G to be GLN, and then now let us consider the tensor product. So, take the natural representation Cn, take the tensor product. So, let us actually compute what if we compute the Casimir operator again with respect to the trace form for this module. So, then you can prove that this is exactly equal to 2n times identity operator plus twice sigma, where sigma is the flipping operator on the tensor product. So, this is actually defined to be operator on the tensor where it switches first component and the second component. So, the transposition 1 2. Okay. So, if we take this Casimir operator then it has this very explicit form. So it's not hard to prove that this sigma is indeed a GLN module map. Okay. Now using this, if we just actually compute, okay, so prove this, then compute the eigenvalues of this Casimir operator. Then if you look at the generalized eigenspace decomposition, okay, so then you can see that, so the primary decomposition of this V comma this operator C trace Cn tensor Cn is going to give you exactly the usual decomposition that we know, that is the sim 2 Cn direct sum the alt 2 Cn. Okay. So we already know that both of them are G modules. So the primary decomposition of this operator, Casimir operator, is going to give you Cn tensor Cn as direct sum of these two representations, okay, as G modules. So this is something very interesting. So it's important to actually understand how given module actually decomposes into G submodules. Okay, so maybe you should actually try to compute these things even for SLN and so on. So there are some natural representation that you can always define, like SLN acts on Cn, SLN acts on Cn tensor Cn, even it acts on k-fold tensor Cn up to k times. Then you can actually take the trace form and then see like what you are getting and so on. Okay, so many examples one will be able to compute. So we will be interested in the tensor product later. So we need to understand how Casimir operators actually act on the tensor product. For that purpose, let us record this proportion, so which will be used later to understand the tensor products. So if we take V and W be two GLN modules. Okay, so again we are only dealing with the finite dimensional modules. So then we can actually consider the tensor product, and with respect to the trace form we can actually define Casimir operators. So now if you think about it, then we have the following relationship. Okay, let's just denote CV tensor W trace to be CV tensor W. So the Casimir operator corresponding to the trace form on this V tensor W is just denoted by CV tensor W. Then it's easy to see that the trace of this divided by the dimension V tensor W, which is we know already dimension V times dimension W. So that is going to be exactly equal to trace of CV divided by dimension V plus the trace of CW divided by dimension W plus 2 divided by n trace of, take this identity matrix and then make it act on V. Okay, so we have this representation. Okay, if we have this map GLN to GLV, so we can actually denote the image by XV or XV. Okay, so then you can see that, so maybe I will drop this vertical line. So you can take this identity element here and then you can look at its how it acts on capital V, and then you can take the trace of that, and then you can also take trace of same identity element acting on W, then you divide by the dimension V times dimension W. Okay, so this is the formula that you get between the trace of C tensor W and all trace of CV and so on. So, in particularly if you know trace of CV, trace of CW and this trace of identity acting on V, identity matrix acting on V and trace of again identity matrix acting on W. So, then we will be able to compute what is trace of CV tensor W. So, this is again some simple computations. So, but let us prove this. So, we have to fix some notations. So, let us actually call the dimension of GLN to be just capital N, which is small n square. So, we have a basis of GLN. So, what we do, we choose this basis such a way that first capital N minus 1 elements actually corresponds to basis of SLN. So, we know that GLN is SLN direct sum this identity matrix. So, if I take this basis, so we choose so that this n minus 1 becomes basis of SLN, and then you set xn to be some multiple of identity. So, we will actually choose the scalar carefully, some multiple we want to choose. So, we will choose later. Okay, actually we can actually choose it to be the dual actually. So, we are interested in the dual. So, okay, let us do the computation and then see what we want to choose. So, we have this basis. Now, we can actually take this to be the dual basis. Of this x1 etc. xn again with respect to the trace form. So, I guess we can take this scalar to be just 1. So, now it is not hard to see this the trace of any x in x in SLN is 0. So, that means, so basically if I take this identity matrix, look at the orthogonal complement with respect to the trace form, that is going to be SLN. So, because of that since x1 etc. x n minus 1 is coming from SLN. So, that will imply that y1 etc. y n minus 1 is coming from SLN again. Okay. So, because they are orthogonal to each other, SLN and this one dimensional center is they are orthogonal to each other. So, now if we just calculate, you can easily see that y n should be exactly. So, basically the value should be b of x n y n should be 1, but this is nothing but trace of identity, and this is going to be some scalar. So, this is so the product. So, this is going to be exactly a times identity. So, this is n a. So, that implies a is just 1 by n. So, this is going to be just 1 by n times identity. Okay. So, now with this let us compute what will happen to the Casimir operator defined on V tensor W. So, let us say its act on the standard basis Vi tensor Vj. So, this is going to be exactly summation xk yk act on V8 tensor Vj. So, let us call this V1 etc. Vn is the standard basis. So, oh sorry, we are given actually two modules V and W. So, we have to fix the basis. So, let us actually fix the basis. So, let us call V1 etc. Vm to be the basis of capital V, and then W1 etc. Wp to be the basis of W. We know that Vi tensor Wj, this becomes basis of V tensor W. So, this is something we are fixing. So, now if you do the calculation, how it acts on the basis element C V tensor W acting on Vi tensor Wj. So, this is going to be given by this. So, this is exactly equal to, because this yk xk, they are going to act as derivation. So, if you just rewrite this is going to be summation xk yk acting on Vi tensor Wj plus yk Vi tensor xk Wj plus xk Vi tensor yk Wj, again plus. So, there will be 4 terms Vi tensor xk yk Wj. So, this is going to be the sum where k ranging from 1 to n, which is n square. So, now you can see that this is exactly the action of Cv on Vi. So, this is going to be Cv acting on Vi tensor Wj plus, so this is going to be giving Vi tensor Cw acting on Wj. So, Vi tensor Cw acting on Wj. So, then we have this these two sums. So, you just write them there, yk Vi tensor xk Wj plus xk Vi tensor yk yk Wj, k ranging from 1 to n. So, this is exactly Cv tensor W acting on Vi tensor Wj. So, now if you think about it, so this is, let us say, call it star. So, if we take the trace of the Cv tensor W, what it is going to be. So, we have computed how it acts on the basis, okay, the indexing set being ij. So, now if you apply it on the basis element, then you have to look for the ijth entry of the coefficient of the basis element Vi tensor Wj in this expression star. Okay. So, if I take the trace, so basically you are going to sum over the diagonal terms. If you think about it, this is exactly the coefficient of the basis element Vi tensor Wj in star, okay, because just the ith coefficient so ij is the tuple where it's indexed on. So, you are looking at the coefficient of that ijth basis element. So, if you just take this expression and then if you just think about it, then you can see that because this is the basis that corresponds to the tensor. So, then that means, so this is going to give you exactly for each j you are going to get corresponding to Cv of Vi. So, you will get exactly the trace of Cv, and for each I you are going to get trace of Cw. So, that means, so this is exactly going to be equal to P times trace of Cv plus M times trace of Cw, and then plus summation k range from 1 to n. So, if you take this expression, you can see that here you will be getting trace of yk, and then here you are getting trace of xk. So, it is the product because it is a tensor product. So, this is exactly trace of ykv times the trace of xkv plus the trace of xkv times the trace of ykv. So, this is what we get from this base. So, now like I said, we have chosen this xi's and yi's to be very specific elements. So, now it is not hard to see that because SLN is indeed equal to its derived algebra. So, that means if we take any element xv where x is coming from SLN, the trace of xv should be 0, okay, because whenever g is being its derived algebra bracket gg, then x comes from g implies the trace of xv is 0 whenever the g acts on the representation capital V. So, this is a small observation. So, if you use that observation, then you can see that whenever we take x and y's coming from that SLN, so the trace of the corresponding elements will become 0. This trace, this trace, this trace, this trace will become 0. So, what survives? Only that identity matrix element. So, basically this is gives you, this is the dimension of W times the trace. So, this is the trace of CV plus dimension V times trace of CW. So, then the place 1 to n minus 1, capital N minus 1 will all vanish. So, only the trace of the identity matrix which survives, that is the identity element acting on V times the trace of identity matrix acting on this sorry, this should be, so this is acting on W. So, this should be W and this should be W. So, this is acting on W plus trace of, again for n, identity matrix acting on V times trace of identity matrix acting on W. So, this is exactly giving you, oh sorry, so xn is the identity, but yn is 1 by n times identity. So, you get 1 by n here and 1 by n here. So, if you put them together, you can see that the trace of C V tensor W is given by dimension W trace CV plus dimension V trace CW plus 2 divided by n trace the identity on V trace identity acting on W. Okay. So, now you rewrite the formula using dimension V tensor W equal to dimension V times dimension W, then you get the original formula. So, then you get this formula. Okay. So, this actually completes the proof. So, we will be using later these formulas to actually understand the tensor product of irreducible representations. Okay. So, this actually kind of completes what I wanted to tell about Casimir operators. Okay, I will stop here. Thank you. I will stop here.